To measure time, astronomers link all observed events to a periodic and uniform process. Solar days change constantly while Earth's rotation relative to distant stars is more stable. Only modern atomic frequency standards achieve the measurement precision of 1 microsecond per year. Different time systems help us accurately determine the life rhythms of our vast universe.
Welcome. We all talk about time, but what is it really? In physics, we have to move past the purely philosophical and get practical. How do we actually measure this thing we call time? That's what we're diving into today. We're going to unpack the fundamental principles we use to construct a physical timescale, which is an absolutely crucial tool for everything from astronomy to experiments in the lab.
So here's our roadmap. We'll begin with the big conceptual challenge. How do you even measure an abstract idea? Then we'll get into the search for a perfect natural clock. From there, we'll see the incredible evolution of our most basic unit, the second. And finally, we'll dissect what a day and a year really mean from a precise astronomical point of view.
All right, let's begin. To really get started, we have to go back to the theoretical bedrock of all this, and that means going back to Newton. You see, his entire formulation of classical mechanics rests on a very specific, very powerful assumption: the existence of an absolute universal time.
What did Newton mean by absolute time? Well, he envisioned it as this perfect, unwavering river. It flows at the exact same rate everywhere in the universe, completely unaffected by anything happening around it. Imagine a single cosmic metronome ticking at a perfectly steady rate for everything, everywhere. Now, it's a fascinating and elegant idea, but for us as physicists, it presents a huge practical problem.
Exactly. How do you put a ruler to a ghost? This very question forces us to move from the purely theoretical to the observable world. In order to create a timescale that we can actually use, we have to anchor the flow of everything we see to some kind of physical process, something that is, ideally, periodic and perfectly uniform.
So the hunt is on. The logical solution is to find some recurring natural phenomenon to act as our standard, our clock. But the moment we start looking out into the universe for this perfect timepiece, nature presents us with a fundamental limitation. And here we face a crucial reality. It turns out there's no such thing as a strictly periodic phenomenon in nature. Nothing. Not a single process in the universe repeats with absolute flawless regularity. So, we're forced to rely on the next best thing, what we call quasi-periodic processes. These are phenomena that are almost perfectly regular, but not quite. So you see the critical distinction. The ideal periodic process is a beautiful theoretical abstraction, a perfect clock that simply doesn't exist. The quasi-periodic process is our physical reality. Things like the Earth's rotation, with all its inherent errors and variations. This means every timescale we construct is fundamentally an approximation. Its accuracy is only as good as the stability of our chosen standard. And, importantly, we can only identify the flaws in our clock when we find an even more stable, more uniform process to measure it against. You know, this continuous search for a more uniform process, for a better clock, is perfectly illustrated by the history of our fundamental unit of time, the second. The definition has progressed in stages, and each one represents a huge leap in precision. We started by using Earth's own rotation as our clock, defining a second as a fraction of a day. But when we realized the Earth's spin is irregular, we shifted our standard to its more stable orbit around the Sun. And finally, we moved from the grand celestial scale all the way down to the quantum level. And this is where we are today, the atomic second. That incredible number. 9,192,631,770 is the exact number of oscillations of radiation from a specific energy transition in a cesium-133 atom, and that is what we now define as 1 second. The precision is staggering. We're talking about an accuracy of about 1 microsecond per year. It's an improvement that is almost impossible to overstate. Okay, so we've established our fundamental unit with incredible accuracy. Now let's deconstruct a more familiar interval, the day. You might think a day is a day, but in astronomy, we learned that its duration is not a single value. In fact, it's entirely dependent on the celestial reference point we choose for measuring one full rotation of the Earth. We really use 3 primary reference points. First, there's the vernal equinox, which is a specific calculated point on the celestial sphere. Second, we have the center of the actual visible sun. And third, we use a theoretical, fictional point called the mean sun, which we imagine moving across the sky at a perfectly uniform rate. Each of these defines a different type of day.
Let's start with the sidereal day. This measures the Earth's rotation with respect to the vernal equinox, which is essentially like measuring it against the backdrop of the distant stars. This is the true rotational period of our planet, one full 360-degree spin.
Now, the true solar day is what you would measure with a sundial. It's the time between two successive noons, when the sun is highest in the sky. But because of Earth's elliptical orbit and its axial tilt, the sun's apparent speed across the sky changes throughout the year. This makes the true solar day non-uniform. Its length actually varies from one day to the next.
Obviously, you can't run a society with clocks that speed up and slow down. So to create a practical clock for civil life, we average out all those variations of the true solar day over an entire year. This gives us the mean solar day, which is what our clocks measure as exactly 24 hours. It's based on that fictional mean sun moving at a constant, predictable rate.
And you're probably seeing the pattern here. This exact same principle, that the definition of a time interval depends completely on the reference frame, applies just as well when we move to our largest common unit of time, the year.
So we have two primary definitions. The tropical year is the time it takes for the sun to return to the same position relative to our seasons, for example, from one vernal equinox to the next. This is the year our calendars are based on. But the sidereal year is the time it takes for the Earth to complete one full 360-degree orbit relative to the distant stars. And because of a slow wobble in Earth's axis called precession, the sidereal year is actually a little bit longer, by about 20 minutes and 24 seconds.
This table really summarizes those key distinctions. You can see the precise non-integer values for the years when they're measured in mean solar days. And notice how they're defined by different astronomical phenomena. The key takeaway is that each of these is a distinct, physically meaningful way to measure time.
So think about this journey we've taken, from the unsteady rotation of our own planet to the quantum oscillations of an atom. It represents a true triumph of measurement science. We have constructed an extraordinarily precise ruler. And yet, this raises a final, profound question I want to leave you with. Has this perfection in measurement brought us any closer to understanding the fundamental nature of time itself? Or have we merely become master craftsmen of a tool used to measure a phenomenon that remains, at its very core, a deep mystery?
Thank you, friends. Strive for understanding and become wiser. See you soon.